generate, to ask each other questions about our disciplines, to really learn more about each other, the basics of each other's disciplines, between the synchronous sessions and online availability for review. Hopefully, we can all come to see the coastal system through a variety of different disciplinary lenses, so we can find new science that we can forge that's less constrained by the historical disciplinary boundaries. So looking ahead to next time, just a quick preview for 2 weeks from today. Antonio Sebastian and Rick Ludick will teach us about coastal flooding, and this will involve terrestrial hydrology and coastal oceanography, and looking forward to that one in a big way. For this week, we've got, well, good news and bad news. Kathy Dello, the North Carolina state climatologist, was on the docket, but she has gotten her vaccine. Yay! And she's under the weather because of that. Less good for us, but we will reschedule, and we'll let you know when that will be rescheduled for. So the other good news is that Miyuki Hino is feeling good and is ready to go. And so Miyuki is a environmental social scientist, which is wonderfully broad. She's in the Department of City and Regional Planning at UNC Chapel Hill, has degrees in chemistry as well as an interdisciplinary, PhD in interdisciplinary environmental science. And so I suspect Miyuki could teach us about a bunch of different disciplines, but we will see what she can fit into a 20 or 25-minute presentation today, and followed by less constrained question and answer than we might otherwise have, and less constrained by time, and never constrained by topic. Any question is good. Any discussion is good. Speaking of questions and discussion, the way we do that is you can send questions in through the chat. Either send it to everybody, and Catherine and Arde will call on you and ask you to unmute and ask your question, or if you would prefer, just send it directly to Catherine and she'll read it anonymously. And with that, I'll turn it over to you, Miyuki.
Thanks, Brad. Thanks for the invitation. I'm excited to get to share with all of you today some of really an entire field of research on the economic impacts of climate hazards. And thanks everyone for joining us. I'm looking forward to the discussion. So as I said, I'll really be talking about a whole field of work today, and this entire literature is really oriented around one big motivating question, which is what are the costs of climate change? This is obviously a very complicated, big question, but it's a really important one, right? Because if on the one hand, we worry about how much it's going to cost to overhaul our electricity grid and to reforest and to get everyone to buy electric vehicles, the other side of that equation is how bad is it going to be if we do nothing? And a lot of this work that I'll be talking about today is really oriented around that other side of the equation. So what is it going to look like if we don't do anything about climate change, if we don't mitigate? What are the ways in which we're going to be affected? So depending on what you're trying to measure the impacts of, it can be fairly straightforward or it can be really tricky. So on the left-hand side here, we have a picture of Harvey, Houston after Hurricane Harvey. And it's pretty straightforward to say that if that flood hadn't happened, none of those houses would be damaged. So all of the costs associated with rebuilding and repairing, those are attributable to the flood. But right, let's say we have a heat wave and it's 100 degrees outside and 100 people go to the hospital. We can't necessarily say that all of those hospitalizations are due to the heat, right? We would expect there to be some number of people that fall ill, even if it weren't 100 degrees. So we have to do a little bit more work to disentangle what was the contribution of that 100-degree day to hospitalizations, and really try to isolate the linkage between the climate hazard on the one hand and this other outcome that we care about on the other hand. So climate econometrics is a set of sort of a research agenda that's emerged very strongly in the past 10 to 20 years, trying to disentangle these relationships between climate and things that we care about, social and economic outcomes that are important. Some of the first work in this space was in agriculture, which of course is both really large economically and very climate sensitive. And so what you're seeing here is basically a dose response curve. We've got a dose of temperature on the x-axis and a response in the form of maize yields on your y-axis. And so you can see that maize becomes very sensitive to temperatures that are above 25 or 30 degrees C. Like we get this big sensitivity on the hot end of the spectrum. And we can take this sort of statistical framework and look at a bunch of other things as well. So here's an example that's from mortality. Again, right, the dose here is temperature, the response is mortality. And you can see when it comes to human mortality, we actually have sensitivity on both sides. We've got increases when it's really cold and increases when it's really hot, which makes sense. That's consistent with our understanding of us being comfortable at a certain specific range of temperatures. We can also look at things that maybe seem a little bit less scary than mortality. So this is how much people swear in tweets, which is also sensitive to temperature, it turns out. So again, people swear about the same amount until it gets to about 25 or 30 degrees C, and then people swear a lot more. And this anger or human sentiment effect has actually been found in a lot of different ways, even crime, violence, mental health. There's a lot of ways in which things we might not expect are sensitive to temperature, and they're actually sensitive at maybe lower temperatures than we would think. Okay, so this is a coastal research network, so we're going to bring this back to the coast here. And what I'm going to do today is I'm going to talk through basically how we get these dose response relationships. And I'm going to use an example project that I did a few years ago, looking at the impacts of high tide flooding to walk through this process. I think most of you in the room are probably know more about high tide flooding than I do. But in case you're not familiar with it, so high tide flooding is coastal flooding that occurs that's separate from storms and big hurricane events. So it often is driven by elevated water levels due to a king tide or wind blowing from a certain direction. And what you tend to see is a couple inches or a foot of water on roadways or in coastal parks. It doesn't tend to be catastrophic, right? We don't tend to see like major infrastructure damage resulting from it. And sometimes it only lasts for a few hours because it can recede when the tide recedes. We don't really know a lot about the impacts of high tide flooding. We don't know much about what it does to the people or the communities that are affected. And this is becoming a growing concern over time because of sea level rise. So here along this axis, you've got a bunch of different NOAA tide gauges. And at each gauge, they've got a designated water level threshold, which they use as a proxy for flooding. And the height of the bars here is showing how many days each year that tide gauge is going above that flood threshold. So you can see pretty clearly that in the 50s and 60s, we were getting 0 to a handful of days each year above that threshold. But that number of days per year above the water level threshold has really, really jumped over time, especially in the mid-Atlantic on the East Coast. And now there are a number of places seeing 40, 50 days per year of flooding pretty regularly. Okay, so the study I'll be talking about today is in Dock Street in Annapolis, Maryland. So Annapolis is located right on the Chesapeake Bay. And Dock Street is shown in this picture on the right. It's this kind of hybrid street parking area. And it's really the center of the tourist historic district of Annapolis. And so people come and park here and they go to these restaurants and retail stores on the right-hand side. This is a satellite view. I just wanted to point out, so the 2 red arrows here are the entrances, and the 2 yellow dots are marking the storm drains, which will become relevant in a few slides. So what we did in Annapolis is we tried to study how high tide floods on Dock Street affect customer visits to that area. So this is a really important part of the city. It's part of the tourism engine. And so it's a serious concern for them when Dock Street's underwater. So we did this through 3 key steps. First, we had to actually figure out when it floods, right? That's obviously an important consideration for studying the effects of flooding. Then we did this dose response causal linkage. So how do floods affect customer visits? And then we looked at the cumulative impacts over the course of a year. So we can say in any given flood, this was the impact, but over the course of the year, this is what we see. And this is how we expect that to change moving forward if we don't do anything about it. Okay, so starting with when does it flood? As I mentioned before, NOAA's tide gauges have these thresholds designated with them, but for any given place, you don't know exactly if that threshold is going to apply. So what we did here is we started by gathering all of the visual evidence we could find of flooding on Dock Street. So we went on Twitter, and one particular business owner regularly supplied us with photos that were conveniently date and time stamped for us of when it's underwater. The city, we partnered with the city on this, and they were fantastic. They gave us a ton of documentation that they had, and during our study, there was actually a flood event. And so they pulled the footage from their CCTV camera and sent it to us. And so we could actually basically see it minute by minute on what the tide gauge was reporting and what we saw in the parking lot, which was really useful. So we used all of that visual documentation to put together this figure. So here, every dot is a day. On the x-axis, we have the total rainfall that day. And on the y-axis, we have the maximum water level recorded on the tide gauge. And we did this for 2 reasons. The first reason was that there are at least some people who thought that this wasn't a sea level driven problem. They thought it was a rain driven problem. So we wanted to make sure that we were in fact catching stuff that was driven just by the water level in the Chesapeake Bay. And the second reason was that we needed to estimate our own flood threshold, right? So we have a tide gauge that's conveniently right around the corner, but we needed to know exactly when water on that tide gauge related to water in the parking lot. So every blue dot here is a day where we have pictures of flooding. So we know for sure that it flooded. The gray dots are days where we don't have documentation. So that could mean, like down here especially, that probably means it didn't flood. So of course we don't have a picture. Up here, it might mean that it flooded and it was in the middle of the night, or nobody decided to tweet it, or a bunch of different reasons why we might not have documentation up here. But as you can see, for sure, we have lots of days of flooding where there was 0 rainfall. So we can be confident that these are driven by what's going on in the bay. And we can draw this sort of empirically estimated flood threshold. This red line, I think ended up being 1.73 feet, where that's the lowest level of water on the tide gauge, where we would start to see water on Dock Street. So we took the water levels above 1.73 feet and split them into 3 categories of minor, moderate, and major flooding. Here we've used LiDAR data to give you a sense of what's underwater in these different categories. So the red shading is stuff that, at least based purely on LiDAR elevation data, would be underwater. And what you can see, the important thing is, right, at minor flooding, this is basically a large puddle. That's how I would describe it. And it's centered right on that storm drain, because what's happening on Dock Street is not that the water is coming in over the edge of the dock. It's coming in through the drainage system and up and out. So we've got basically a large puddle that expands as the water level gets higher to moderate and to major. Basically, the whole front half of the parking lot's underwater. It's very important to be clear that this is what we would call major high tide flooding. This is not major flooding by any means. This half of the parking lot's underwater, the rest of the city is basically dry. So these are all categories of non-catastrophic, relatively small floods. So basically, we've now got a way to relate the tide gauge directly to these flood categories. And so we can assign every hour in our data set to either no flooding or minor, moderate, or major flooding based on the water levels. So then the next step is figuring out how floods affect customer visits. So I think it might be helpful to just stop for a second and think about how we tease out cause and effect more generally, right? Ideally, what we would do is we would have identical setups, treat one experimental group, have a bunch of control groups, treat them all the same way, and then compare the outcomes. So ideally, what we would do is we would have like 8 dock streets and flood a few of them when we wanted to, and then measure the differences, right? But we can't do that for multiple reasons. There aren't multiple dock streets, and also we can't flood things whenever we want to. So we have to do something else. So what we do is we use flooding as a natural experiment as opposed to a controlled experiment. And we're going to compare dock street to itself over time. So we compare dock street when it's flooded to dock street when it's not flooded. And we have to do some specific statistical adjustments to make that a valid comparison. So what we have in our data set is parking meter records of customer visits to dock street for about 1.5 years. And each of those hours, we know a water level and a precipitation measurement. So we're going to run a regression. And the outcome we care about is visits. And we've got these 3 treatment groups of the minor flood, moderate flood, and major flood. But visits, of course, are going to fluctuate for lots of reasons other than flooding. So we need to account for that in some way. So what we do is we're going to add these controls for things that might be driving visits at different times. And so in particular here, we're going to control for rainfall because if it's raining, people are just less likely to go out and do stuff. We're going to control for the time of the day. So this is the hour measures because there are going to be more people out at noon than at 8 a.m. We adjust for the day of the week, more people on a Saturday than a Tuesday, and then also the month. Especially in a tourist context, right? There's going to be significant seasonal variation. So what's really, really important to take away from this is the way we're measuring the impacts of flooding is we're comparing visits at noon on a Tuesday in October when it's flooded to visits at noon on a Tuesday in October when it's not flooded. And what we're taking advantage of is the fact that it's not that tidal flooding is totally random, right? But it is random whether or not it's flooding at 2 p.m. on this day or 4 p.m. on Wednesday, right? So there's this random component of tides and floods that we're taking advantage of here to do this natural experiment. Okay, so this is what this looks like in mathematical regression form. What we care about here are these 3 coefficients. So beta 1, beta 2, and beta 3 are going to tell us how much visits are changing in these different flood stages. And when we do the math, what we get out is that visits drop quite a bit at all levels of flooding. So at minor flooding, we're seeing about 35% drops in visits. That goes up to about 70% at moderate flooding and about 90% at major flooding. So to be clear, 0 here is the no flooded, not flooded baseline. That's business as usual. And so we're seeing declines from those normal levels of activity. One interesting thing we saw here is that the flood effects actually do not disappear instantly. So even after we would expect there to be no water on Dock Street, we still see abnormally low visits. So it takes a little bit of time for visits to recover after a flood event. And so when we think about the cumulative effects, right, this is really important because the impacts on visits last actually longer quite often than the flood itself is lasting. Okay, so one very reasonable next question would be, maybe this doesn't matter because people are just parking nearby and walking over to Dock Street. So we wanted to look into that. So what we did was we took visits to this blue box. This is the nearest alternative parking area. And we basically ran the same regression because we thought that if people are going here instead, we'd actually see positive displacement, right? So we'd see a bunch more visits in this other parking spot area than when Dock Street's flooded. So we tested for that, and we see no measurable difference in visits here to that alternative spot. So that gives us good reason to think that this is in fact meaningful lost visits to this area, given that public transit is not a very common way of getting to this particular destination. Okay, so now we know the effects of any given hour that's flooded. What does this look like over the course of a year? So one neat thing with this dose-response relationship is that we can basically statistically undo flooding, right? Because we have what's observed and we can simulate the counterfactual. And so what we've done here is we've taken what we observed in 2017, which was about 165,000 visits. And we took our water levels in 2017 and just lowered them little by little, right? So as we lower them, we take floods away and we regain visits. And so when we go all the way down about a foot lower than 2017, we have no flood hours and about 168,000 visits. And as we bump sea levels up, we increase flooding, we lose visits, and we estimate that in 2017, we saw about 3,000 fewer visits. That equates to about $100,000 in revenue losses across maybe, I think it was 13 businesses, 10 to 15 businesses that we considered. And those revenue losses can be attributed to the incidence of high tide floods on Dock Street in 2017. We can also push sea levels higher, right, and move into the future. So this portion of the graph is what I just showed you. And this blue part is what happens when we hit fast forward and bump sea levels up. And what we can see is that we really are just starting to see the impacts of these floods in a measurable way, but that they really increase steeply as sea levels rise. And so absent adaptation, so assuming that the relationship between water levels and visits stays the same through time, with a foot of sea level rise, Dock Street would see about a quarter fewer people each year than they currently do. Okay, so I'm taking advantage of the fact that I can go over time, and I'm going to talk a little bit about what I think is really cool about this statistical approach, which is what it can tell us about adaptation. And so in the context of, we've been talking a lot about the negative effects of climate hazards, but we can also use this to study what happens when we adapt. So in this context, when we adapt, what we would expect to see is these coefficients going to zero, right? We'd expect the sensitivity to go down to the different water levels. And what we can actually do is estimate, right? We can count up how many visits would be saved by investing in these adaptation measures. And then we can use that to compare against how much it would cost to do those things in the first place. And we haven't done this in Dock Street. They are talking a lot about adaptation and they care a lot about it, but they haven't made any substantial investments yet. But in other sectors, we actually have seen adaptation already. So this is, again, the mortality example that I showed you earlier. We've got this sensitivity on both sides of the curve to temperature. And what we'd expect to see if there was adaptation taking place, we'd expect to see this curve get flatter, right? Less sensitivity to temperature. And in fact, that's what we do see. So here is in red, the dose response curve from 1930 through the 50s. And in yellow is the 60s through 2004. And so you can see literally that we are getting less sensitive to temperature, probably because of air conditioning and heating and better medical practices. In other sectors, they've looked at this in other ways. So this is in the crop yield space. So on the left, they compared the sensitivity in different areas of the US, thinking that if you're hotter to start with, maybe you'd have less sensitivity to temperature than if you're colder in general. And we don't see big differences across the different parts of the US. They've also compared places that warmed really fast, where you would expect people to not have time to respond, right? Like if your climate's moving really quickly, you don't have time to learn and adapt in the same way as if it's moving slowly. But again, here we see, these are not statistically distinguishable. And so it actually seems like we're not really adapting to become less sensitive to temperature in this particular space. So I think there's really cool opportunities to quantify some of the benefits or lack thereof of adaptation measures using these same frameworks that for the most part have been focused on looking at costs so far. Okay, so I'm going to wrap up. The key takeaways here. So first, these econometric approaches can help us uncover the costs of climate hazards that would be difficult to observe otherwise. So we don't always need to do this kind of thing, but sometimes it can be very helpful to do so. The natural experiments are taking advantage of some form of randomness in weather and hazard incidents to quantify the effects. And so we really need the precise timing of that flood to be random. We need it to be random that it was 75 degrees today and not 68 degrees today, because that's how we get the experiment part of the natural experiment. And finally, we can take these same statistical frameworks and use them to look at adaptation. And I think that that's a neat emerging part of this field of work. Oops. And I will stop there. Thanks.
Thanks, Miyuki. Okay. I have one question that came directly to me in the chat. Marty, do you want to go ahead and ask your question?
Sure. First, I just want to say Miyuki does a fantastic presentation, and having followed a good amount of this climate econometrics work for the last 15 or so years, I think you really hit the mark in terms of describing what it's about for a very general audience, and I just congratulate you for that. So I want to kind of dig more into the adaptation issue. I really like the way your alternative location analysis is a sort of a placebo analysis of sorts, or really an exploration of whether the tourists themselves are adapting. And so I guess my question is, what do we make of the quantitative stuff that comes out of this particular study and these studies in general, when there might be very large scale changes in the future as adaptive measures? So for instance, the community might build an elevated parking structure or something, which would be sort of game changing in a way, but we don't have that in samples. So how do we think about those possibilities in assessing future climate damages in this space?
Yeah, that's a really good question. And I think one of the subtle things that made this study in Annapolis doable, which would have been harder in other places, is that the flooding was so localized. Because if you have flooding in 8 different parts of your city all at the same time, then it's actually even harder to figure out what's going on right in this one place. And so similarly, when you think about huge amounts of sea level rise, they might be able to put a parking structure in there that's elevated. They're actually, I haven't been tracking this extremely recently, but the last I heard, there was discussion of an underground parking garage underneath a hotel in that spot, which I'm sure that engineering is possible, but I think would be challenging. But anyway, you could think about an elevated parking structure, but that might just mean that that stays dry when everything else around it goes underwater, right? As we start talking about feet of sea level rise. So I think that the adaptation quantification here is quite useful for thinking about adaptation that's small enough that it's hard to see otherwise. So individual behavioral changes, how much can maybe like businesses themselves do to continue bringing customers in somehow when it's flooded. AC adoption, right? In the mortality context, it's small scale changes that add up into a larger scale thing that you're seeing in the relationships. But it does feel to me that the really big infrastructure changes that are at least in discussions for coastal places, so much is changing when we do things like that, that it would be very hard to draw conclusions from what we've seen to date about the impacts of those things.
Okay, Paige, go ahead with your question.
Hi, Miyuki. I have two questions for you. One is, I'm not familiar with this literature, should we be thinking about correlated flooding events in the area? So like maybe another street is also flooded, so you can't even get to Dock Street. And two, thinking about like what this tells us about adaptation and learning. I'm curious if we should be thinking about the tourists as, are they driving there and realizing they can't park and go home, or are you also thinking about their forming expectations about the flood? And I'm wondering, I wonder if you've thought about how to disentangle like the avoidance from learning about floods over time. Thanks for your talk. Really enjoyed it.
Thanks, Paige. Yes, I think so. In this particular context, I have reasonable, from everything I know, this is much lower lying than the rest of the city. So the key transport corridors aren't affected. But you can imagine for sure, like in the Outer Banks, that a single flood that could be in a different location, right, that knocks out part of the transportation network would materialize in much larger geographic effects. And so I think the question of what's the unit that you want to, that is treated, right, that I think is very context specific. So for sure, that's a concern in general. On the learning side, so I did about 20 interviews with people in and around Dock Street, and it was fascinating because I think that there was a very wide range of mental models for what was causing the flooding, how often it was happening, and why. But it was sort of, I would say there wasn't proactive anticipation of when it might, this type of like relatively small flood, there was not, nobody had a tide calendar, right? Nobody was looking at like when they should expect something like this to happen. The hotels also weren't warning guests, for instance, was one question we asked. They did say sometimes people would call them and say like, I can't get there. And they would say, just like, give it a couple hours, try again later. So I think eventually we could see things like that where in a lot of different ways. So either customers learning, I think locals in Annapolis obviously can just come at different times. Like they shift the timing of their visits to do what they want to do. With tourists, they have less of that opportunity. But I guess it was not apparent to me that there was a lot of active learning happening yet that would change this relationship in a meaningful way. But that definitely could emerge soon.
Okay, thanks for that, Miyuki. Brad, you want to go ahead and ask your question?
Well, I'm more on possible adaptation and thinking longer term as there get to be more and more days per year of flooding in this and other similar places, like you showed that the days per year of flooding in a lot of different locations in the US. Seems like adaptations like which parking lot we go to are going to become less useful. And what range of adaptations do you think people might entertain?
That's a good question. I think it is one that Catherine and I have been thinking a lot about these days, thinking about what's flooding where and what do people do about it. Depending on the connectedness of the geography, I think there are like relatively small scale strategic things, a combination of backflow preventers on the stormwater pipes, plus pumps if you need them, plus elevating your bulkheads, like your coastal edges just a little bit. And that at least gives you time, depending on the place, it gives you a different amount of time. I think there are, of course, questions around how long do these places just make sense to maintain, period, as places where people rely on for their daily, for their livelihoods. And it's just a very hard question. It's a very hard question to answer and a very hard conversation to have. I do think one of the interesting trade-offs that a lot of places are making at the moment are thinking about, do we prepare for the really big event, or do we invest in stopping these small frequent events? And in a lot of ways, the engineering responses are quite different. And so I know, in speaking with the people in Annapolis, that they are just sort of like crossing their fingers and hoping they don't get hit by a big storm, because all of their money right now is going into dealing with this kind of flooding. And so they're trying to, they've elevated the dock a little bit. They're trying to overhaul some of the infrastructure and put in 2 big pumps. But that means that, those are going to be useful with the high tide events, but that's not going to be very useful when any kind of major storm comes through. So I just think there's a lot of trade-offs, that there are a lot of tough decisions, I think, coming down the pike. But hopefully by looking at stuff like this and trying to understand where the social and economic impacts of even small scale floods are greatest, that can at least help communities target appropriately, right? That can at least point to them that this particular road linkage has effects over this large geographic space. So let's try to focus on this, even though it might flood slightly less often than this other kind of neighborhood, smaller road. We need to start understanding what the true impacts are of the disruptions at different places, because they're not going to be able to do everything. And we need that evidence to help them target.
I see Rick is waving his hand. Calling on you, Rick.
Well, thank you. I will add my voice of how much I enjoyed your talk. Do you have a sense that people have a concept of what information they would like to have so that they can make better decisions going forward? I mean, it seems like a lot of it is what I see is people saying, okay, here's what it's looking like. How can I adapt? How can I mitigate that? Typically, again, with engineering decisions or things. But do you think that, for example, property values, the willingness for someone to purchase a business in an area like this, or all of those things are being influenced by someone saying, I need to know this in order for me to make a decision as to whether to stay here, or in particular, whether to come here?
Yeah, another really good question. I think for people and property choices, it is extremely hard for an individual buyer to know if and how often a place floods before they buy the house. So you have to have quite large amounts of local knowledge to know that like this is the street that floods all the time, not one block over, right? Because these are small, right? They're relatively small, they're relatively short-lived. And given how little people know about, for instance, their flood zone, which has to be in the disclosure form, it's just really hard to distinguish, for people to distinguish between this place floods once every 50 years and this place floods 50 times a year. That information is not widely available, so I think it's hard. And I know that in some conversations I've had, these really slight elevation gradients make a big difference. And one step into your store can mean the difference between water in your store 15 times a year and never. And in the conversations I've had with people who deal with this, they've like become more appreciative of the small elevation gradients in their street because of the flooding, right? They're like, I have noticed that it starts over here and it moves in this direction. But that is not information that they knew before they were there all the time and seeing it. And I think that the recurrent flooding is especially hard to kind of, from a scientific perspective, it's hard to warn people about because it can be changed, right? If people invest in pumps and backflow preventers and overhaul some infrastructure, then it would change. And so you don't really want to tell people like this place is going to flood 60 days a year in 15 years because you don't, like, based on current infrastructure, sure, but you don't know what that looks like going forward. So I think there's a real communication challenge there. For both potential business locations and residential locations. However, I do think that the recurrence of flooding, just annoying frequent flooding, is much more compelling to people as a reason to leave than the occasional major threat. And so in terms of people, for instance, who want buyouts, people who want to get out of floodplains really desperately, I tend to hear that from people who, like just in interviews and in newspaper articles, that tends to come from people who are like, the water is at my front door 8 times a year, not I flooded once really badly 6 years ago. So I think there are quite different behavioral, it seems to be like fairly different in the way people respond to small, frequent, annoying things and more psychologically distant big things.
Okay, we had a clarification question. Let's see if I can find it. It had to do with how did you relate parking lot, or how did you translate visits to parking lots to revenue losses?
Yeah, I glossed over that because it's a little hand wavy. So we did 2 things. So first, the city tried to do a version of this study. And so they went to all of the stores that flood, and they actually tried to get daily revenues from the stores themselves on, it wasn't quite the way we were going to do it, but they were like, it flooded on April 11th this year, but not last year. So give me your daily revenues on April 11th from the past 3 years, and we'll compare those. Unfortunately, they only got like 5 businesses to give them that information. So we had some data on, and then of course they only had like a few dates that we then had to relate to our flood measures, right? So we basically took their estimates of revenue losses from those specific dates and then compared them to what we had. And we saw that revenues dropped a little bit less than visits dropped. So visits could drop 2%, revenues would drop more like 1 to 1.5%. And then we extrapolated that relationship for all of the revenue for those 12 to 13 businesses. So we did know the total annual revenues. And so basically we had a dose response curve for visits, we adjusted it for revenue, and then we took the total annual revenue and used that.
Okay, I think we have time. Well, we have lots of time, but I don't want to wear you out. Laura, do you want to ask your question? And then unless anybody else or any other questions come in, Marty, you can wrap it up.
Sure, Miyuki, that was great. Thank you. I'll add my voice to that too. So you talked about adaptation and you showed some really nice examples of how you could remeasure the dose response curve after adaptation to see a change. And I was just wondering about the role of model simulation in assisting a community to think about how various different adaptations might affect some of the economic parameters that they're most interested in, and was hoping you might speak to that a little bit. I could think, there are some adaptations that are pretty straightforward, like you mentioned, putting out information about when flooding might happen, and people might adjust around it in a way that wouldn't affect things quite as significantly as if they didn't know. That's a lower cost intervention, but raising that parking lot would be much bigger. Are there ways to bring model simulations in to help understand the benefits of different adaptations so they could be compared?
Yeah, definitely. Well, I think model simulations can be helpful in lots of different contexts, but especially in contexts where we're outside of the historical record. And so this even becomes a problem when extrapolating beyond our sample sea levels, right? We only have sea levels that go to a certain height, and we know that they're going to go higher in the future. And so using models to think about those, both, I think, more extreme scenarios and also combinations of things that also are very hard to study based on past observation explicitly. I think models can be really helpful in both of those contexts. I think, yeah, and I actually didn't talk about this in the presentation, but certainly what we did was the simplest possible way of thinking about sea levels going up and down, right? We didn't think about changes in variability in sea levels over time. We didn't think about the rainfall component. We didn't think about potential erosion. Like, we did the simplest possible thing, which was like, let's nudge everything up a little and take everything back down a little. And obviously that is not a great representation of the real world. And that means that we might be dramatically underestimating the frequency of flooding and how that's going to change in the future. And so for that reason as well, we would want to be more detailed in the physical mechanisms, right, of what's going on with the flooding, and to be able to kind of simulate what's going to happen in the future a little bit better. So I think there are a lot of different ways in which other approaches and extensions of this would be quite valuable.
And can I just follow up real briefly to say, do you have the sense from working with this community that they're interested in approaches like that could be brought to bear on what they might choose to do or choose not to do?
They are, so the City of Annapolis, I guess it's been a few years since I was working with them. They're very concerned. They want to act. They know this is a problem. And I think, and so they were great partners for us because they were really useful in helping us put together the data and work with us to interpret it. I think when it comes to what to do about it, so this they've actually used the study in an application to FEMA to get money to do something about it. So I think there's that side of it, which is by providing some of this quantitative evidence, communities can then be empowered to take it and say, this is how big this problem is for us.
Right.
We need to respond. So in that sense, I hope it was at least a little bit useful to them. When it comes to what to do about it, I think, to be totally honest, it's such a value-based, there's just what people care about and what their vision is for the future of these parts of their town is so, so important. And And I think ultimately there are a lot of things that cannot be measured well and in the econometric framework that are at least as important, if not more, in those types of decisions. And so I think it can help, but it's certainly not the only thing that is needed to inform those choices.
Well put. Thanks.
All right, Marty, you can, oh, wait, Dylan, please ask
Yeah.
your question.
Okay, I have a jumpy internet, so if I freeze, don't make fun of my frozen face.
No promises.
We'll take a picture.
More accolades. That was a wonderful talk, really coherent and understandable. I loved it. I have just a kind of a detailed question that I'm a little curious about. It just occurred to me. In your regression, you should be able to find out those revenue losses. How would that compare to a sort of less rainy versus a very rainy summer or year? Are we kind of way less than that or kind of approaching something like that?
That's interesting. So we do have a coefficient on rainfall. And I can't extrapolate it to annual mentally because I don't know how much rain they get over the course of a year. There was a negative effect. We showed it, we plotted it at some point as the equivalent negative effect of 1 inch of rainfall in an hour, was something like I want to say 10 to 15% drop in visits. But what I would have to do is grab the precipitation relationship and figure out how many inches per hour there were across the year and add that up. And that I have not done, so I don't know for sure.
Just strikes me to be kind of interesting there's so much discussion about these sunny day floods because they're quite a different disturbance than raininess, which we can't control and we don't really know, and it's coming sort of randomly. And it'd just be interesting to compare the community's responses to the two things. That strikes me as interesting.
Yeah, and also the possibility that on a normal tide that wouldn't cause flooding, a little bit of rain does cause flooding. So you do have to worry about both of them together at the same time. But yeah, I didn't make that comparison. That's a good idea though.
Catherine, do we still have time for me to ask a quick last question?
Yeah, go for it.
Okay, so I want to do something a little integrative here because one of the cool things that's striking about this presentation is the way you were able to get really high temporal resolution data from those parking meters to say something about this highly temporally resolved climate phenomenon. And that's, I mean, of course, the identification of the natural experiment is the key there, but also the availability of both of those types of data are critical. And when we do a lot of this work, and we heard Satya Gopalakrishnan talk in this series about real estate data and the use of that to try to understand effects of beach width and other coastal related amenities. One of the things that we're plagued with is at the geographic specificity we care about, the data are quite sparse. There are very few repeat sales transactions, whereas with parking meters, you got it like kind of through. So I guess without asking you to sort of reveal all of the things that you might be working on to get scooped, what's your advice on identifying like these kinds of climate natural experiments that really do this integration of the humans and the natural phenomena? Like how do you think about these problems? How do you find these cool big data kinds of things? And so it's maybe a hard question to end on, but I thought it's a little integrative and maybe take a stab, see what you say.
Yeah, so it's a great question. And in this context, both sides of the equation are tricky, right? The measurement of actual flood incidents is tricky. And what's something that you can measure that's changing on such short timeframes as flooding is changing. Both of those sides are pretty hard. And so on the measurement of flooding side, I think there's perhaps some potential in some of the very high frequency satellite imagery that is now available. I don't think it would necessarily, it's not going to be taken at the time that you need, but it could help you extrapolate the relationship between different weather forces and the presence of water somewhere. I think it's probably only feasible in places that are flooding all the time. So where you'd have enough images of water essentially in those places. Catherine and I are working on sensors at the moment to actually detect flood presence in real time and report that back. Because I do think that that really high temporal resolution information on what's underwater and when is critically important to understanding what's going on coasts, and we really don't have it. I mean, truly, like I really believe that we collectively are sort of underestimating how often, and the geographic extent of what's underwater frequently. And I think we need to do better at that. The social scientists need to sort of grasp that a little bit better before we throw stuff into our regressions that tells us, maybe stuff that we're not fully understanding. So that I do think is a huge problem. And then on the dependent variable side, local partners are just so valuable. And I really, really value working with community groups and local officials who want to work on this problem and want to understand things better. Because I think there are a variety of ways to look at this. You could actually take business revenues, right, for companies that, for establishments that are recording that on a high resolution basis. You can look at road traffic, right, trip traffic, which is increasingly available in small geographies and on small time scales. There are, depending on your application, ways to use social media to do some of these things, cell phone mobility data. So there are, I think there are some like really big data approaches, but truly, I think the most interesting stuff is going to come from like understanding what matters to the people who are experiencing it and getting the data with them and working from there. Because it seems to me that you just have a much better understanding of where the data is coming from in those contexts that you don't have with some of these like anonymized cell phone based sources. So that's just a shameless plug that if you live in a place that has this problem, reach out to me and Catherine and tell us about your problems. And we're excited to work with you on it.
Love the plug. Okay, I think that's it for today. This was great discussion. I think probably the best that we've had in D101 so far. So thanks for your time, Miyuki. And we hope to see you guys in 2 weeks for Antonia Sebastian's talk and Rick Ludick's talk on coastal flooding and flood hazards. All right, have a good week, y'all.
Thank you, Miyuki.
Thank you, Miyuki.